So today's lecturer is Johanna Erdmenger from the University of Würzburg, and Johanna will be talking about insights from quantum field theory and AdS CFT for machine learning. So thanks.
Yeah, thanks a lot, Gabriel. So thanks to the organizers for inviting me to this very thrilling program, making connections between apparently very distant topics, which is black holes, number theory, and machine learning. And so in the spirit, my talk tries to look for connections between things which apparently are not so closely connected. So it's going to be a very synthetical talk in the sense of drawing connections. And so in particular, I'm just going to start with quantum field theory and AdS CFT and tell you a little bit how techniques there can be used to actually improve machine learning. So I should say my approach to machine learning here will be that I'm going to use methods from quantum field theory and AdS CFT to improve or understand machine learning. I'm not going to use machine learning to study anything in physics. So the order is a bit the other way around, and maybe other people will think about it. Okay, so I'm in Würzburg. It's a university town in the north of Bavaria, in a part called Franconia, and it has nice classes, in particular this one, which I can see from the balcony of my apartment. So I chose this as a teaser. Okay, so let's start with the motivation, because it's really about putting things together. And so this is a talk in the context of the AdS CFT correspondence, which was proposed by Valentina now already 26 years ago. And so the starting point is that, as most of you probably know, it's really a duality which is rooted in string theory. It comes from considering B branes, in particular D3 branes, if we want to talk about any support of Mills theory. And so what it provides to us is a duality between quantum field theory on one hand side and a gravity in a hyperbolic space with a negative cosmological constant on the other side. And so, of course, black holes play an important role due to the holographic principle, because these two theories, although one is at the boundary of the other, have the same amount of degrees of freedom per unit. And so this is very akin to black holes. And so let me give you my definition of the word duality, which can mean very different things in physics and mathematics. And so my working definition is a rather physics-oriented definition of the word duality is when you start with some physical system, which in the original case of the AdS CFT correspondence are the three branes, where then consider the situation that we have one theory which, depending on your case, is given by an action or a Hamiltonian with some degree of freedom, and then which describes the physical system, and then there's another theory with an action, different action or Hamiltonian with different degrees of freedom, and it happens that this theory also describes the physical system. Well, then obviously there must be a relation between the two theories, and so this relation we refer to as a duality. That's my definition of the word duality. And so AdS CFT is very special because it's the first duality relating a quantum field theory to a theory with gravity. In that sense, it's very special. And so then, of course, one important question that arises: can we formulate this principle more generally than in string theory? Although string theory gives us such a good hand. Okay. The motivation for that basically started by this work by Julius-Maximilians-Universität in 2006, and which added a new flavor to the AdS CFT correspondence in the sense that they showed that in the context of AdS CFT, you have a duality between entanglement entropy in the quantum field theory and a minimal surface in the gravity theory. And so in lower dimensions, you can actually really do the calculation as done by Cardi and Conversely of the entanglement entropy, and then calculate this minimal surface according to this prescription, and you really get exactly the same result from the calculation. And so that's a rather spectacular relation between entanglement, which is a quantum concept, and geometry. And that sparked a number of ideas, and so many people are working with from very different perspectives, and I think later in the program they will also be talked about this. There's this idea of space-time reconstruction. Can you reconstruct the higher dimensional space from the data that you have given at the boundary? And so another topic that arose in this course is to consider further quantum information measures beyond entanglement entropy to study duality and learn something about the latent quantum behavior of black holes in antimatter space and so on. Here, just to give two, one is complexity. That tells you if you start from a initial state, how many operations, unitary operations, you have to apply to get some final state. So that's a well-known measure in quantum information theory, and nowadays quite a lot of discussion on how to implement this in the context, even at the level of having duals of individual gates or unitary transformation. Something I'm going to mention more today is the so-called relative entropy, which you can see here for in the quantum theory. So it's really an entropy that measures the difference, or in some sense assigns a distance between two probability distributions given by two density matrices, rho 0 and rho 1. And so later this will play an important role in the context of applying some of these ideas to learning. However, of course, machine learning is something which is classical. So what I'm going to say about information methods will be classical, and well, that's not necessarily a bad thing. And makes things simpler. But I mean, you know, I would like to emphasize that this motivation really comes from this quantum information. Okay, so the two big questions which arise, which I would like to address partially in this talk, is, okay, I mentioned already, so string theory gave us the AdS CFT correspondence. There is very strong motivation from considering brains. But given all these developments that apparently quantum quantities such as entanglement are related to geometric objects, can we actually construct more general examples of gauge gravity duality beyond string theory, and maybe even use this later to further understanding about the original version by and so later this will play an important role in the context. And the other thing I'm going to address, and where I have of course nothing quite concrete example, is to use the concept of information geometry also in the context of machine learning. So I should say this word information geometry is much older than the AdS CFT correspondence. I think there's somebody called Amari who has actually a very nice book on this already from the 70s. So actually combining geometry with probability, this is not a very new idea, but it also had some very nice insights, led to some very nice insights into AdS CFT that could have been done much earlier, because this is really a topic which has been established, which was established about 50 years ago. And all right, so after introducing all these big questions, let me give you an overview of what I'm going to tell you. So, the first topic on which I'm going to spend some time is this using information geometry for machine learning. So in the sense that we would like to improve machine learning, we would like to learn how the networks are trained, and can we quantify this learning procedure by using some geometrical concepts. Namely, relative entropy will play a role there, because it can give you a distance measure between different probability distributions. So that's what we're going to use. And so this is the first example which I'm going to start with, and I'm going to spend quite some time. The other two topics, okay, I have many things to say about them, but I'm not sure if I really get to everything, but it's not necessary for the purpose of this talk. So one topic I've also been working on, which is not directly related to machine learning, but more to this quantum aspect of using information to learn something about quantum gravity in the context of the AdS CFT correspondence. And so Würzburg is a place where there are many quantum physicists, so they are very much topological informators, geometric phases, Berry phases, and so it was natural to look at those also in the context of AdS CFT, and also there's a very nice connection to the story of the operator algebras or von Neumann algebras that were considered quite a lot recently. So after the machine learning experts, I I would like to see a little bit more. So, and then at the end, if I have time in this idea of constructing a duality without using string theory, I would like to show you a little bit about this discrete holography, so which is the idea of establishing a holographic duality not on a continuous manifold, but rather on a regular tiling of antidecitor spaces. And well, we didn't get to the end yet, but we have some very nice insights about how to construct theories in the bulk and upper boundary. And so I'm going to show you a little bit of how we got and what are the remaining open questions here. The motivation here, again, there's some motivation from machine learning, although I didn't get into really studying this yet, but I think there's a lot of opportunity. The so-called hyperbolic neural networks. So these are networks which have a kind of tree-like structure. So in the sense that the number of nodes grows exponentially, and that's of course exactly what you have in the hyperbolic geometry. Given all the knowledge that's around about AdS spaces, which have been accumulated, it seems natural that to understand these networks. I don't have very much to say about this, but this discrete homography idea is certainly your first step of having a network of nodes in this context. Okay, so that's the plan. Any remarks? Okay, so then let me start, and then we start with the first topic. So I should say the first topic doesn't make use of AdS spaces. It's essentially quantity theory and statistical mechanics, but nevertheless, there's some inspiration from these information methods. Okay, so the first topic is to make some progress towards quantifying information flows using the classical version of the entropy, and so in particular making some use of some insight in the context of RG techniques in quantum theory and applying them to neural networks. And in particular, what we're going to do is to compare a neural network with just an Ising only. So the idea is to quantify the learning capacity of neural networks using concepts from quantum theory. I put AdS CFT into brackets because that's more related to this hyperbolic network, but the first part here of the talk is exclusively about just ordinary network and stuff. Okay, so I'm very grateful to my two collaborators, Johanna and Prof, who introduced me to this topic, and so what I'm going to talk about in this paper. And as I said, the relative entropy is a concept which is being used in the topic of information geometry already for a very long period. And so in that context, it's referred to as the Hilbert-Leibler divergence. Okay, in physical terms, we would think of this as a distance between two probability distributions. However, there's not really, it's not necessary to define a metric. And you can define a metric, but it's not necessary to define a metric. So if you want to use the word distance, you have to define a metric, which we don't necessarily do. So the mathematically correct terms divergence, which is more general than this. Okay, so here we see this distance. So there is a distance between two classical probability distributions, which is of this one, which is of the type of an entropy, of course. And so this is what we're going to use. And so this divergence quantifies how much the target distribution Q differs from an initial distribution Q. Mm-hmm. I should speak up. Okay. All right. Let me try. Okay, so now the idea is that we're going to calculate this Hilbert-Leibler divergence on the one hand side for just a 1D Ising model, which is the simplest possibility that we can do, and look at how it behaves, and then we will calculate it for a very simple neural network, and we will compare the two and see what happens. So, the simplest possible thing is to have a spin chain with a one-dimensional Ising model. So we have a plane of nodes, and they are spin variable sigma, and they can point either up or down. And so this is our Hamiltonian that we start with. And so we use this. So we want to use some idea of renormalisation group, and so we use this most simple possibility of applying RG, which is this so-called decimation RG. which just means that we fix every second of these spins to a particular value. Okay, so this is called decimation RG, and so here's our original partition function for the entire Hilbert space of this model. So I should emphasize that this is called classical Ising model, and then we essentially fix the ones in the space H prime, and then here there's a sum over the complement, and so then we introduce new variables sigma prime, such that the partition function that we get coincides with the one at the beginning. And also for the probability distribution, we find a new probability distribution in terms of new variables, which essentially have the harmonical structure. Okay, so it really just means fixing every second spin. And then we calculate the relative entropy by plugging these results for P and P prime into the formula which I had on the previous slide. There's one slight normalization issue because we would like to normalize the probability distribution to 1 at every step. And so that leads to this term of, this is the dimension of the complement of the original Hilbert space without this removing X prime. And this is necessary to make sure that the probability distributions are normalized to 1 at every step. And then you can calculate the probability. I mean, you can really do it analytically in terms of your case, and there's some processing which appearing about, I'm not going into the detail, but essentially what we get is the Hamiltonian in this form, and then this normalization term.
Yes, but yeah, you want to find like classes. All right, what you're doing this is where you divide through by 11.
Well, I think it's done as a formula of infinite lux.
Oh, sorry. Sorry. It's on.
Yeah.
It's off. Can you all hear me?
I thought, yeah. You're even louder than myself.
I asked, is this done in infinite lattice or a finite lattice?
I think we've just been the most simple possible thing and not looking at any boundary conditions or finite size effects. So it's just looking at the RG steps. So
Pretty periodic.
yeah, we can put periodic boundary conditions. Yeah, exactly. Okay, so
sorry, it's relevant because then when you do the KL divergence between probability distributions.
Yeah.
Okay, so probability distribution, let's say n spins.
Yeah.
And then so normally how it's traditionally defined, you would say it's a probability on n spins with a probability on another one with n spins. Now you're finding now a probability distribution between different numbers and degrees of freedom. So KL is not traditionally defined for that.
That's exactly why I was talking about this normalization point. Okay, very good point. I mean, I think this is what this term is supposed to take care of.
But does that mean that it can be negative?
Right, that's exactly what I wanted to show on this slide.
Okay.
So if I don't do, yeah, exactly. That's the thing. If I don't do this normalization, then you indeed get something negative, but this we consider slightly unphysical. And so, but if we make sure that every step we normalize the probability distribution, the interval to be 1, then we actually get a positive result. Okay, so that's exactly what's shown on this slide. So here we have the KL divergence for the one as a function of real space decimation set. And so what we do is we change the value of the coupling to K. So, and if we don't take care of this issue, as we say, we get something negative, that's slightly unphysical, but with this additional normalization time, we do get a positive behavior. And so what's the physics that we extract from this? So we start from 0, and then of course, when we start the book, there's only one probability distribution, so the distance is 0. And then, so what happens if you now perform the renormalisation steps, the P prime and P, they're going to get more and more different. And so what we see is that the behavior that it increases and then it plateaus to some value. And so here we did this for different values of the coupling, and the stronger the coupling, the bigger the difference between the two probability distributions. And so this has something to do with counting the information that is stored in the system. And so what we actually see is that the stronger the coupling, the larger the information stored in the correlation. So that's really what we extract from these two. So you can really see if the coupling is very large, there's a bigger difference between the distribution we start with and the one we end. And and of course, the bigger the coupling, the more correlations there are, and so they will actually be able to store the information. Okay. So that's essentially what we can learn from this very, very simple model. I mean, you can also do it in 2 dimensions, but already in 2 dimensions, there's this issue that this definition doesn't really work. And so it's simple approximations, and then the calculations get more involved. But for the 1D, I think model, we get this behavior. So, and the method I'm going to have now, I'm going to look at some neural nets, but the KA divergence will have a very similar behavior, not a function of the AdS set, but of the depth of the network. And so what the information that you can see from the physical behavior, so from correlating and storing information, we can also see it in the neural net. So that's where I'm heading. Okay, so I probably not everybody's really familiar with how a network works. So and of course there are many different networks around, and I'm just focusing on one particular kind. And so which is the so-called feed-forward random neural net. And so here from Wikipedia, this is a simple picture. So we have layers of nodes, and so you start with an input layer, and then there can be a large number of hidden layers. There's only one in this picture, but there can be many, and then there's an output layer. And so you feed some input data, which are essentially some real numbers, and then they get processed in a way that I'm going to explain now. And then at the end, you get some output. Again, in terms of real numbers. And then to actually, there's this important feature of training the network. So this is what is different from the Ising. I mean, principally the Ising model is also a network, but it's an untrained network. Okay. So then we start with some data. One possibility is that many people use is the so-called endless data. So it is some data from the National Bureau of Standards in the US, and they have 60,000 times written the numbers between 0 and 1. And so then you can train the network to read these numbers. And so of course, the way it's done is that you feed some data. So these are pixels, so it's 28 by 28 pixels, which makes 784. So you start with 784 nodes, and so you see whether it's black or white in the square, and then the network processes information, and then you get some result again for the same values, and then you just compare them to each other, and you have a least mean square approach. Essentially, I mean, of course, there are many sophisticated details which I'm jumping over, and based on this mean square, you tune the parameters in the model to make it do this better the next time around. And so then there's something for the epoch, which is just feeding through the data once, comparing, feeding the results through, adjusting the parameters of the model, and then redoing it. So that's called an epoch. Okay, so there are many networks, but to be kind of similar to what this Ising model does, we use feed-forward random neural networks. So which means that feed-forward means that every node is only connected to the node in the next layer. And so then we have the layers are labeled by the L, and so there's a certain number of them, and in each level we have a certain number of nodes. And so essentially then we have a map, which is so it gives you these Z's, which are called pre-activation. So the Z is labeled by, so it's a neuron in the else layer. And so then there's here this kind of linear map, which so y is the input in level before, and then so this is for the weight, and this is a bias, it's a kind of offset with the point. And then this was very linear, but it actually becomes quite non-linear because the value y on the level before you fix to be a non-linear function of the activations on the pre-activations on the next layer. Okay. So this means that in this case, the simplest case, the function phi will be a time, so which is clearly a non-linear function. Okay, and then so we will also consider this called random networks, which means that the weights and biases, so weights and biases are the W in these, there will be randomly distributed, but we will do this in a very simple way by just looking at Gaussian. Okay, so that every level W and V level will be given by a graph. Okay, so and so I have a very nice teaching and his master he did exactly that, and so that's what his input, and then the network was trained, and after doing this 50 times, this is the output. And it looks quite similar, and so but this is just the training, and it's not identifying new, it's just comparing output with different things. Quite a lot, but okay.
But for AdS, you need two.
Yeah,
You get
yeah.
perfectly good results with two.
Okay, maybe can we come back to
Unless you get good
Yeah.
results with two. The more complexity, then you may need to go back. So C bars.
Yeah.
But maybe only 3 or 4.
We took quite some more, and well, okay, so also we were inspired by this work by some people who work at Google, and they must have had a very big computer, much bigger than our Würzburg University computer. So I'm showing some pictures of them where they had an incredible depth, and we had certainly less, or results much more coarse-grained. But the question of which depth we have now will be, this is exactly what I'm going to talk about now, because there will be a relation to physics. And so you can see that, well, essentially, the network cannot be trained if the depth exceeds the correlation length. So that's what this is the main message I want to get across. And then, of course, in principle, you would like to get depths as big as you possibly can, because it will be, the more layers you have, the more accurate the learning will be. But there's some limitations, and that's actually where the comparison with the Ising model will come in. Okay, let me go through this slide. Okay, so we have this map with this tangent involved here, and so we take W and these to be Gaussian distributed, and then you can easily check that if W and D have a Gaussian distribution, then Z will also have a Gaussian distribution. Okay, now you can do something very physics inspired, so I'm quoting the result of this paper now. So, that you can calculate the correlation length, where these A's and B's now label 2 different inputs to the same network. Okay, so these X's are the Y0s, the ones that start at this level. Okay, so you put two different initial data, and then you go to level L. And you can calculate this quadratic object, which essentially you can show when it gives you a correlation length when you start with it. I will show some more formula in it. Okay, and actually there will be a phase transition, which is indicated by a diverging correlation length, just as you have for the two Ising ones. But okay, so let me emphasize again this point. This is the important point of the network can be trained is the depth of the correlation. And so, okay, so again, this is a network from these authors from Google with an extremely good precision and depth and a lot of computer time. I don't have our plot, but it looks much more crude. I can show it to you if you like, and then you can look at the figures. But so the physics, okay, so these figures are taken from this paper. So the physics is that there's a phase diagram, which is really something that we know from the generalising model. So so the phase is now given by the standard deviation or the variance, by the variances of the W's and the V's. Okay, so and in particular, so these are the initial values that we start with for at the 0 step. Okay, and so there's a phase diagram and there's an ordered and there is a chaotic phase, which we can show. And so the chaotic phase means that if you have the correlations tend to diverge, whereas in the ordered phase, differences between the solutions tends to be washed out. And none of them are very good for learning. Okay, so if everything is obvious that something is chaotic and it's not very good for learning. But on the other hand, if it's too ordered, it's also not good for learning. Okay, because you want to, the network to be different from your randomly chosen initial data. So, and actually, that's actually the result of the paper, that the learning is the best if you are close to this critical line. And so this is the phase diagram, and then so in this data there is so the lighter the colors, the better. And so that line is to 6 times the correlation thing. And so then you see that there's a essentially a phase like this that we come into the very beginning, where the learning ability is the best. And that's precisely where this this criterion that
Same example with the numbers.
yeah.
The number of layers, is that the depth or the so this L,
Yeah, the L is the number of layers.
is there, what is the optimal choice there? I mean, you said 2 is already good and then it becomes always better, or
No, it's not always better. So normally the cost is the deeper you go,
yes,
there's an exponential blow up in compute time. Because in backpropagation, you
Yeah.
have to go to all the possible places in common.
so from
Goes
this,
backwards. So but also it's also more likely you'll end up in a local minimum. So your optimization strategy has to be very careful. So although we've spoken there about learning, in order to do the backpropagation to get the best thing, you need a clever optimizer. And the deeper you go, the harder that is also to find. So I guess in principle, the expressibility of the network goes up, but the ability to find the thing that you want goes down.
Yeah.
and then the optimum would be a 2 already.
No, I'm just saying. In the case of MNIST,
Okay, so
that just needs 2, and I'll give you 98% in about 5 minutes.
okay, sorry, I think my message is a different one. Okay, first, if a given set of data, you have a given, but here I really want to make this connection to physics. So I want to say, this is the main method. So the depth must be smaller than the correlation length. Otherwise, I mean, there's a kind of physics inside. So it's correlation length the biggest that you possibly to get really large networks that give you good training. So that's what I want to say. So for this one very simple example with this MNIST, we can do it very low level number of levels, but then of course if you have a more complicated task, you want more.
I just ask about that
Yeah.
correlation length.
Yeah.
We'll just get to the previous slide.
Yeah.
So it's the correlations between. I'm showing you what it is. The correlation between. It's pre-activation from. I think because it's not, you look at the pre-activated.
Yeah.
What's the sum of the y's? Are they what are the y's again?
Well, that's the one.
That's the ones in there from the previous layer.
Yeah, it's a kind of little retroactively defined. It's called pre-activation. I mean, okay. So this is a function of the z. It's a bit defined in a kind of backward way. I agree, but so this is essentially tangent of the one in the previous layer.
So it's like, okay, so it's
Yeah.
But the y's have got activation to.
Yeah. So there's a nested
the previous
structure.
layers.
Yeah.
The previous layers neurons.
Yeah.
Running out.
Yeah.
And it's basically the expectation value of the.
Yeah.
But is there an octagonal part to that? I'm sorry, I'm trying to understand.
Yeah, I think
there is. I can't see the labels A and B in the next slide.
A and B are different inputs. So this is I chose an input A or input B.
So I've got the vector.
So the correlation means that I start from two different inputs.
Right. So I put an input vector x1, which has got size n.
Yeah.
I put another input vector 2.
Yeah.
And then I look at the neural activations down at layer L.
Yeah, exactly.
For those two different inputs.
Yeah.
And then you calculate that thing.
Yeah, exactly.
So I see. So it's telling you the distance in neurons for the two different things. But then do I sum? But what's the input? But then there's an input dependence on that.
Yes, there is. Yeah.
So then, when you talk about the correlation,
well, okay, so
it depends on the inputs I choose.
Yeah, but so the thing is that what they do is in this paper is to take the number of neurons to infinity.
No, even so, that's fine.
Then you're
going to get your tangent curve. But before you do that, just I mean, it's not one step back to this thing. Sorry, it seems so important what this correlation is, because when you say the training depends on. So is it some notion that you've got a typical set of two things? Because I could imagine a data set where I've got 100,000 things that are very similar. One thing that's just anomalous and really out there. And then I calculate the correlation length of the thing that's really out there. And go, oh no, that's a huge correlation length. Or how do I pick the two things from which I then determine the correlation length, which then is the statement about depth? Because you've got a statement about depth compared to a length, but it's not a single length, it's a length for all pairs in the data set.
Yeah, I agree. Okay. Let me move, maybe we can talk a little more.
Sure.
Johanna, sorry, one question before we move on. So this rule that you stated between the correlation length and the depth, is that an empirically observed rule, or do you have some theory to back it up?
Careful. I mean, we should look at this paper. I would say it's empirically observed so far, but I mean, there's quite a lot of this done by these people, which I cited here. So maybe we should look again at what we calculated. But I would say it's just the level of empirical observation. So I think it would be very nice to actually prove that 6 times the correlation length gives you precisely this region where the training works best. So that was actually the motivation for what we did, but we didn't quite succeed, but we learned something. This is what I want to show to you next. Okay. All right, maybe let me not go to the detail. I mean, you can go to a very large system and you can change from a sum to a dot integral. And then, so the important point is now this, that we started to calculate the relative entropy for distributions in the different layers. So remember that we have this random two-forward network, so we have a Gaussian at every level. And so what we are going to do is so starting with some initial distributions to calculate the relative entropy just elected from the formula and then to be close to the algorithm. And so the thing is, it becomes very nested, and that's why you need a computer to actually calculate this. Here, this is also going from the 0 to the first level, the calculation is pretty straightforward. So, so you have the variances of the two distributions, and these are the mean of the two distributions. Okay, so the first step is very simple to do, but then in the next step it becomes quite involved because of this nonlinear structure, and it becomes very nested. And
well, wait, but now you've gone to an infinite. You say you've gone to an infinite number of things, but then that's known that produces a Gaussian random process, right? Because the infinite width limits.
Okay, but yes, we work with Gaussian.
And so that Gaussian random process.
Yeah.
And then people know that, and then you get what's called the neural tangent curve. And the neural tangent curve will then produce.
Okay. Then we do something slightly different. Okay, then we can put.
You've got that KL divergence of a hyperbolic space, which tells you that it's Gaussian. In the previous slide, your KL in the last one, you've got 1 over sigma squared plus mu squared. So that's a hyperbolic space.
Okay, but so I know you're absolutely right. It's going to be simple. Nevertheless, if you go to the next step, the formula will be already the entire slide because you have this method structure. So I agree, it's a super simple example because it's Gaussian, and that's probably the reason that we didn't get as far as we wanted. I think we agree. But nevertheless, I think it's quite instructive to see so. And you're also going to get a lot more happening. This is just going from the zero to the first layer, but if you go to the next, you have to, go back every layer and it's recursive and it becomes quite involved. So, okay, the only message I want to get across now is, okay, so we use, and this is also the CFAR data, which is work. I think that also has color information, not just black and white, that's where data for it. And okay, so again, we plotted the tail reference versus the depth. Now for different measure of this individual variance of the way here. And so right, the thing I would like to point out, it looks very similar to this one, the Ising model. Okay, so instead of the AdS steps, now you have the layer, and here again is the tail divergence, and so this is the unplane case, and this is the plane case, and you see that it is a monotonic behavior, and it starts from 0 because at the beginning, of course, the two distributions are the same, and then it grows very quickly, but already after 6 layers or so, it's actually asymptote to a constant value. So I mean, this is the message. It looks very similar to what we did for the Ising model. Okay. And so that's very interesting. Of course, what we would like to have seen that okay. So here with these values of the variance of the weights, we actually go through the space permutation. Okay, so we move. Sorry. We move through this line. But unfortunately, nothing happens. Okay, but okay, you might say this is clear because everything is Gaussian. Okay, but okay, so I mean, the result is insensitive to the phase transition because everything is Gaussian, and okay, but nevertheless, even so, I think it's quite interesting to see this analogy to the one we already want. So this gives some motivation to look more into that. And of course, what we'd like to do now is to do something slightly less to actually be able to characterize exactly where the answer to your question, so that then we can actually hopefully quantify what we want.
I think if the antidotes went almost all the way up to 1.
Yes.
Here they go.
Yes.
Because you make me go.
Good question. I mean, here, of course, okay, it's a good question what these numbers actually mean. Okay, I have to I would be lucky to really draw some information from the absolute value, but maybe, yeah, I have to look at because of the probability distribution also more or less. It's a good question.
I mean, it's because you've not solved it properly in the sense of, I mean, that's not criticism. What I mean is, in the training, the fact that, well, why is the KL divergence going up as you add layers. The chaos.
Yeah, because at the beginning, it's very simple thing that you see. At the beginning, you start with if you're on your layer 1, then they are the same. So you start at 0. Then you train one level, then it's better something should happen. Start with some random data. And the message is that if you already after 6 layers, it outputs to a particular value. The thing is, because it's Gaussian, it could just be a steady state. And then just maybe this measure is not good enough to see exactly what happens inside this layer. You can just maybe move things around, but the distribution remains the same. So,
this would argue that you're doing worse by adding layers, because the KL, you're doing the KL divergence between the distribution of emmets and the distribution of the net.
No. No. I'm doing a distribution between the initial layer and okay.
Oh, the initial layer. And the final layer.
Yeah. No.
Okay, that's right. All the initial layer and the final layer.
Yeah. Well, the given layer.
All right. Okay.
Yeah.
Ah, right. Okay.
Yeah. So it just means the learning happens in the first 6 layers, and then it just
Then nothing happens.
Yeah. Okay, but
Okay, great.
So okay, let me try to summarize the physics of this. Here's the summary of it. I have not much more to say about this than this very simple beginning, but okay, so beginning and it gives us some questions for the future. So okay, it shows similar behavior. This KLM version shows similar behavior in the ID mode and the network. And so, this may potentially be used as a starting point to improve the training networks. However, of course, so there's a big however here. At the moment, this is too simplistic because the KLM diversion is not sensitive to the case of this. Probably because of the growth in nature, and so there's also you are receiving off the turn, and also then actually use steady state. Okay, so another thing is that, as I told before, I can calculate the relative entropy for the ID model. It's essentially just the difference of the expectation values of the Hamiltonians. Okay, so it's sensitive to the collective behavior, but not really to the correlations. But the correlations is what you would need for making statements about the correlation thing. So that's a general statement, and then there's a more the statement more related to this particular example is that the relative entity is just the function of standard deviation of the Gaussian distribution compared. And okay, so as I said, there might be some steady state behavior and things around by the distribution. So that's the thing. Okay, so you see, it's a starting point. You can use some physics to learn something about machine learning, and so the main message is okay. This is a message for the future. At least this simple example shows some ideas that could be followed to make progress here to find a measure which gives you quantitative information about these correlations, and such that you can use this to improve the network design.
Sorry, I'm completely ignorant. Just listening at your computer. Sorry. Apologies.
That's stage transformation. But hold it or not, nothing changed.
Oh, I just talk. Okay, apologies. So I'm a complete ignorance. So apologies, but just listening at your conclusion, can I infer from your last comments on relative entropy that you may need more, allow me to use the word, fine graining in the difference between the probability distributions to access these correlations, but these measures are known, as you know. So in principle, if you were to compute these things, you would be able to let the training process to.
Okay, so I think this
yeah, exactly. No, I was referring exactly to higher moments. So Rene-like quantities that know about the full distribution of the eigenvalues. Everything is classical here. So all about the piece. Is this what you are alluding to? Okay. Yeah. Thanks.
Things or
No. I'm not judging your work. I'm just trying to learn actually and understand. No. Sorry, David, I'm not proposing anything, but you know, this is like, I'm sorry for trivializing the discussion. This is like when people in our community insist about talking entanglement entropy. I mean, clearly the difference between two density matrices is not captured by entanglement entropy, which is just a number. I'm giving you some density metrics that can always be diagonalized. So I'm giving you n eigenvalues. If you really want to tell the difference between the n eigenvalues, you need to have something that is sensitive to the n values, not just a single function. So if you want to reconstruct the entire difference, the entanglement entropy, no one denies for bipartite systems that it's a measurement of correlation, but you may need a full set of Renyi entropies if you want to, in order to study the. Yes, sorry, yes, that's right. So I'm not suggesting anything there, David. But I think that the ideas that Johanna is mentioning is suggesting that you could use these higher cumulants or correlation functions in our language. But if you are really interested in tuning a little bit more. Exactly, sorry. I just wanted to check that I got your message. Yes.
Okay, good. All right, let me move on to the second part of my talk, which is about something completely different. And so far, there is no machine learning here. Okay, but okay. So this is all I have to say about machine learning. But okay, maybe it gives you some indication what the questions are. Okay. All right. Now I'm going to talk more about black holes and also wormholes and more about AdS CFT. And again, the relation is that some concepts that quantify information are relevant for making statements about physics or about gravity. All right. So in particular, I'm going to look at Berry phases, and so what I'm going to do, I'm going to pick a very simple example, not the one the Ising model, but just two interacting spin-half particles. And there we can develop a lot of mathematical techniques that can be used in the context of these von Neumann algebras for black holes and so this is also very popular research area. So I thought that would be the okay. So just a quick teaser, and I go into more details. So wormholes. So I'm first going to consider very low dimensional models. So they provide a relation between entanglement and geometry, so there's kind of PR to PR. This is also based on some work by Hermann van Linde, who had a very nice paper showing how the concept of a wormhole is also present in the simple quantum mechanics model. So then these Berry phases provide a geometrical picture of how to use the freedom entanglement. So in that sense, it's also it's not relevant for machine learning directly with these classical. Nevertheless, I think because I have these nice ideas of using some physics to quantify information in this kind of aspect of information. And so using this, we have a new approach to this called factorization. So I'm going to say very quickly what the factorization is to get everybody on the same page. And so we have an approach that in a kind of final bundle geometric action approach, and this helps to again quantifying this information. Okay, there's a very nice relational story of the von Neumann algebra that has recently been considered in the context of black holes in the AdS spaces, and so essentially the question here is to define entanglement, or to define the entanglement entropy. We use the definition of a phrase which is speaking like quantum theory you don't have because you need a cut off. So it's more one of these questions in algebraic quantum theory. And as the work that we have is work to show that this requires a vanishing of this particular geometric phases. I mostly focus on this spin-half model, but we can also do the same for any non-dimension height. Okay, so this is some work I did recently also with some colleagues in Chapter physics from Dresden in our joint big grant of the excellence cluster in the German research landscape. And okay, so these are postdocs and students in my work. And we had a series of papers, especially the one on algebra for recently. Okay, so the setting is to look at a black hole in an anti-zeta space in global coordinates, which means that we have a non-traversable wormhole. And okay, so the observer can just jump into the wormhole, but they cannot get out. And so time goes up on this side and down on that side. And so it's an internal black hole. And what will be very important here is that there's a singularity in the time coordinate due to these different time directions. So the time-like killing vector switches sign up the horizon. The two observers that jump in, they will disagree on in which direction the time points, and that leads to a particular similarity and also to a so-called non-exact syntactic form. And that will be very relevant for these phases that I'm mentioning. Okay, so already a long time ago, so Martina suggested that so that the eternal black hole is equal to two copies of the boundary CFT, which are entangled in a so-called Conversely double state. So that's the purification of a thermal state of one CFT. So you take a basis of space in the two sides of your wormhole and you combine this with the energy eigenvalue. So and if you trace over the basis of one of the two theories, you get a thermal density matrix for the other one. And so that leads to this famous PR story, which is a relation between an entanglement and geometry. So it fits into the context of what I said at the beginning. And so ER refers to the entanglement and ER refers to the wormhole. So the idea is that two entangled CFTs with ER correlations are connected to a wormhole. So that's the postulate, and which describes the duality in the setting where you have one CFT on one side and another CFT on the other side. Okay, so now what's the factorization puzzle? Okay, if you have two CFTs and you just, without any notion of AdS CFT, take two copies of them, then they have disjoint Hilbert spaces since there's no interaction between them. And so then the total Hilbert space is just this Hilbert product. And on the other hand, if you were able to have a quantum gravity theory for this interior theory, then it's just one theory with one Hilbert space and should not factor. And so there's an apparent contradiction. And as I told you, there have been, of course, on one hand side using these von Neumann algebras, but also in our case with the Berry phases, we can actually make this problem very precise and say exactly what should be done to address it if one day we have a full theory of quantum gravity. Okay, so a nice comment here is what we stated by Hermann. So you can have wormhole-like structures already in quantum mechanics systems just from the integration if you look at correlation functions of the partition function. So again, you start with a partition function, and so this you can write a kind of half integral where you introduce some generalized coordinates and momenta, which have a particular symplectic form in the phase space. And then the integration region is a disk, and so in most general ways, the partition function on the disk will look like. Now, if this symplectic form is exact, then we can use Stokes' theorem, which is written here, and then turn everything into the integral just over the boundary space. But if the symplectic form is not exact, then you can't do that, and so the integration region remains this entire disk. And so now, if we calculate in the last line, if we calculate correlation functions for several insertions of this partition functions, then your integration region will have this wormhole-like structure. And so if you have two of them, you have a wormhole here. In this case of 4, you have this kind of structure with 4. Okay, so in this already shows that the geometry of the integration region has something to do with presence of wormholes in some very basic sense.
So I'm just trying to understand what is the geometry? Because you've got time, the quantum mechanics systems.
Yeah, but okay, so beta. So this is the Euclidean version where you compactify time in the circle.
Yeah.
So the time essentially goes around the boundary here. It's a Euclidean.
Yeah, I think I'm just sort of trying to understand what sense it is in quantum mechanics. In the sense that.
Well, I mean, you have a Hamiltonian, you write this Euclidean level, I think. I mean, you can do this for say, a harmonic oscillator. You can have harmonic oscillators on the two sides. I will show you, we do this now with two spins. Okay, so now there's a beautiful mathematical formalism for geometric phases. Which is based on this so-called Maurer-Paton form, which is a connection on the group manifold, which can be defined for any element of this group. And so it looks like this. And in a quantum mechanics setting now, so we can define a so-called Berry connection, which is the ground state expectation value of this Maurer-Paton form. So describe what is the ground state of our quantum mechanical system. And if we have a connection, we can also define a character which involves this so-called theory of Potsdam symplectic form that we get from the Maurer-Paton form. And okay, this can have some parameters. And the Berry phase, then in this case, will just be the integral over the character. Okay, so I'm going to draw some connection with the von Neumann algebra, so which has been around almost 100 years. And very recently by this group of different authors, this is very prominent in the CFT right now for the many people interested in this. So they have used this concept of von Neumann algebra, which is a concept of algebraic quantificity, which was designed originally by von Neumann for classifying operator algebra systems with respect to their entanglement properties. And so this has been now used in precisely this context for other things, and many other questions in quantum pharmacy. So essentially what von Neumann said that there's three types of these operator algebras. So the first type is where there is a well-defined density matrix in a space. So that's if your Hilbert space is finite, which is kind of obvious. So in all quantum mechanics systems, we have this. And essentially the operator algebra admits reducible in this case. And then now there are two types which are more involved. And so there's type 2 means that there is a way of defining a break function rule, but it does not act reducibly. So that's some kind of intermediate case. And the type 3 is that you don't have any break description. And so that would be the case for any quantity really, because I mean we always need a cutoff to renormalize or to write down the entanglement entropy. Also the Takenagi formula or Kadi-Calabrese, there's always a cutoff inside. So in that sense, in this kind of algebraic sense, there's no limits in that case. I will show you. I mean, there's not some very obvious one, but in this context of the black holes, there will actually be one. Okay. So now what I'm going to do is I will do something extremely simple and take a simple toy model, which in this case is just a system of two interacting spins with a half particles. And so I have a Hamiltonian, so this is the interaction between the two spins, and then on top of that, one of the two spins is a magnetic field. So you can, for instance, think of a Riemann interaction in a hydrogen atom, so essentially the electron field is a magnetic field, but not necessarily the photon. Okay, so this is our Hamiltonian, and so we can solve this linear equation in this case, and the ground state looks like this. So alpha is now just a parameter that involves the magnetic field and the coupling here. Okay, and then you can also show that the Hilbert space, the projected Hilbert space, that is that we look at all the space in Hilbert space that come the same phase in the sense that they have the same probability density. In this case, it's actually 2 Okay, and then you can use the so-called Schmidt decomposition, which is just writing this in some orthogonal basis, and in this very simple case, we just come over the different up and down possibilities, and there are 4 of them, and they have particular coefficients that I didn't. Okay. So, and now, although this is such a simple model, we can see some very beautiful structure in the Hilbert space that actually is very much related to this factorization problem. And it depends also on the entanglement entropy or related to it. So we can calculate the entanglement entropy for the system. And you can just calculate what it is. And it depends on this alpha, which is the ratio of the magnetic field and the coupling constant. And then you can now distinguish various cases, for instance, the recoupling case. So when the two spins don't interact, so that remember this example of the wormhole where you have two CFTs on each side, and just you can consider every side as being one of these two spins. So if they don't interact in this case, then there's no entanglement, and then the entanglement entropy vanishes. And then you can define something which is the so-called entanglement orbit. So that's the subspace of the Hilbert space in which all the spaces have the same entanglement entropy. And in this case, we can show it's actually factorized. Okay, so there's a CP1 for the one spin and a CP1 for the other, and you have this factorized product. Then, on the other hand, if you consider a maximal entanglement, which in this case means that in this very simple example that the entanglement entropy is just element 2. So that actually happens when very, very large, and this means that this alpha goes to infinity, I think. Yeah, so very, very large here, so that we insert it into this alpha, and then in that case, you can actually see that in that case, the space is not factored. It's arbitrary. And for intermediate entanglement, there's various other spaces which may look topological of this. So even in this very simple example, so in this case, the parameter that we turn is switching on an interaction. In one case, you have a factored structure, and here you have a non-factored structure. So that's quite nice. And then, so then also now we can relate the very case in the von Neumann. And in this case, it's a type 1 von Neumann algebra because it's a quantum mechanical system. So we can calculate the very case from the symplectic volume of the entanglement orbit. Okay, I already mentioned symplectic forms. So so essentially the reduced density matrix will be the square of this P, and then you can find the orbit, and every there will be SU2 transformations that you can apply. And then you can find the very connection and the very curvature, which is the symplectic form. And then the very case, as I showed before, integrated over the symplectic form, and it takes this value, which is your very case. And so for the maximally entangled state, alpha is 0, and then also this very case function. Okay, and that's interesting because now, so that was in this paper, we can show that the trace function that we have applying it to a commutator is proportional to the geometric space. So a trace function there is a function that is cyclic in its argument. So we did a function that does this for two elements of the operator algebra, and if we apply our function to the expectation value of an operator in our ground state, we precisely find that this function vanishes precisely when the very case vanishes. Okay, so that means if we take the maximally entangled state, we have the state for which we can define this trace in an unambiguous way. Okay, in this quantum mechanical model, this is relatively simple, and but on the other hand, we can also do this for a wormhole in low dimensions. And there again, so as I showed before, we get the non-exact symplectic form from this very connection, but here in this case, the non-exact symplectic form comes from the fact that there's the similarity in the time point. And so essentially, so the mass or the temperature of the electron black hole will give rise to the global filling vector not being present in this wormhole. So essentially now there's you have a Hamiltonian on the left hand side, a Hamiltonian on the right hand side, and so if you evolve by the difference between the two, this is just the symmetry. But if you evolve the sum of the two, this is actually something that will lead to the similarity. And so I mean you have time translation as a boundary, which appear in this phase here. So essentially that gives you the P1 times P1 to the P. And there's one bulk isometry which comes from the difference of the two Hamiltonians. And so the bulk modular space of traffic utility is one again, and it's parameterized by the parameter delta, which is the difference between the two. So if one observer jumps into this end of the wormhole and another here, they will disagree on the time and so the difference between the time to delta. And this delta is now precisely the parameter of your various connection if you look at the TSV state. And then you can really actually insert the actual definition of the TSV state, and then you can calculate the very phase, and then you see that is not equal to 0, and so it's proportional to the geometric phase of the bulk modular space, and because that's singular, you have a non-zero very phase, and that precisely tells you that you cannot define it twice, and so it also means that you have this non-factorized geometry. And so now coming back to Gabriel's question, so the idea would now of course be to do this for in the quantum mechanical settings, and of course the values papers where you will have written, and one essential point here is that if you start, so these black holes, they will have a type 3 algebra. So the place is not defined, but so it was argued in the paper by Whitman, if you do 1 over n correction, then you get a type 2 algebra with a vanishing center, and that allows for a well-defined wave function for just one particular state. Now, this statement we can rephrase in our approach of the geometric phases. So if there's non-factorization, which is the case for these wormholes, then we have a non-zero geometric phase. And this means you can't define a place, and then we have a type 3 for Neumann algebra. On the other hand, for the maximally entangled state, the geometric phase vanishes, and then we get type 2. So in the case of the black holes, that will be the case where the temperature of the black holes goes to infinity. Okay, of course, that doesn't really, that doesn't really solve it's a kind of way out, but really what you would like to see that if you have full control of quantum gravity, then you should be able to see this factorization in a consistent way. Here is just some kind of odd limiting case where the mass of the black hole goes to 0. Yeah. Yes. Yeah, that's definitely the case. That's also the case in our yeah. Okay. Let me look at time. Okay, so let me make a few comments first. So there's also a relation to the missing information. In the sense that when there's a non-exact inflection point, then it means there's no global section for the entire system, which means that we need different coordinate patterns to cover the entire space. And also then you can make a connection to the left and right side of your wormhole again, because so an observer in one coordinate patch has more information about the other. So these different coordinate patches, they already occur for this very simple example of the two spins, okay? Because there's one transformation where you can change it. You cannot cover your sphere with one coordinate patch, and then when you're in one coordinate patch, you don't have information about the other. So again, it's a very nice connection to this idea of information with this kind of the guideline of this talk, that you really have the missing information can be mapped to something geometrical, in the sense that if you're in one of the coordinate patches on this sphere on your switch sphere, you cannot see what happens in the other one. Okay, so this again gives you a way of quantifying information in this context. Okay, I would like to talk a little bit also about my third topic, but let me very quickly say, so if anybody's interested, we can talk about this later, that this very phase structure, okay, I showed you this very simple example of two spins, but you can also do it for reversal symmetry, for instance. You can define very sizes for conformal symmetry. It's very difficult. However, Oblak, who did it just for a one-sided without the relation to the enhancement that we later in the very first. And then so there's a very beautiful mathematical background we use for all the so and then you can construct the gravity dual of this, and then essentially you have a non-trivial holonomy. Okay, so if this is now your AdS wormhole, you can look at the side. Okay, so you look into one end of the wormhole and you see the other end. And then there's a non-trivial holonomy by going around the other side. And this holonomy will actually couple the geometric actions on the two sides of the wormhole. And then again you have a non-factorization. Okay. All right, for the last 10 minutes or so, let me go to my third topic. Okay, so this is all about doing the same story that I told you for the very simple example for CFT. But in the last few minutes, let me go to the third topic, which, okay, so this is motivated by two of the questions that I wrote at the beginning. One is, can we establish a holographic duality on a hyperbolic tiling in the sense of having a duality beyond string theory, which encodes all these ideas of information and geometry. On the other hand, this is also a kind of first step. I have no idea exactly how, but this is certainly something I'm interested to look at the hyperbolic neural net, and there's a lot of information from AdS that you can use. I mean, there are many papers already by computer scientists who write down scalar products between different levels, making sure that you have this curvature in the metric inside the scalar product. And it's very good to have, if you want to have a network with some exponentially growing or decreasing number of nodes. And so the geometry is already used, but I think there's a lot of opportunity for people in AdS CFT there that we can use with one to make some more statements about these networks. And you know, again, in this question of having some quantification of how good the training works, I think there's a possibility where we can potentially do something. Okay, but here I have nothing to say about the hyperbolic networks so far. Just mentioned that it's a really interesting topic, and you know, I invite you to look for those. And for these people of you interested in AdS CFT, you will recognize many interesting metrics that they are very familiar to us in that context. Okay, so but here I just want to ask the question: can we have an example of a holographic duality beyond entropy? And so the idea is that we just look at the regular tiling of a hyperbolic space, and then of course there's no guiding principle. Okay, so apart from we want the same number of degrees of freedom, we want the same symmetries as we have in AdS CFT for this particular geometry. Okay, so here's some papers that our group will recently worked in this topic. Okay, so and what is fun about this topic is that it really branches out into many areas of physics and mathematics. So one are the hyperbolic neural networks that I already mentioned, but there's some very interesting questions in mathematical physics to actually determine the asymptotic boundary manifold, or maybe it's not a manifold, I mean just the set. Okay, there's even some possibility of having some fractals at the boundary. There was some work by mathematicians showing that actually the real Takanagi formula also holds in fractal dimensions. So then the whole correspondence intervals. So this is also interesting. And then there's some applications in convex matter physics in electric circuits. So there's even some colleagues of mine who actually build electric circuits in this hyperbolic space. Then, of course, this would be an approach to again introduce 1 over n corrections in the AdS correspondence, and there's also some work in multi-state theory on these networks. Okay, so there's plenty, and so let me just show you here as a appetizer. So one of my colleagues actually has an AdS2 space in his office. So this is by these authors here, but there was some prior work by this collaboration here. So there's some macro resonators and some hyperbolic lattice. And other possibilities is to have electric circuits with capacitors and inductances. And okay. So again, I mean, they put in an electromagnetic wave at the boundary, and then you study what happens in the body. Okay, so that sounds like a lot of fun, but of course we can possibly say quite a lot about these things. So so the first way is, how do we start? Okay, so we take a constant slice of AdS3, and then we have a tiling, and so the tilings they're fixed by 2 numbers. So P and Q, and so it means you have Q regular looking at each vertex. And so then these P's and Q's, they will appear in many places. Okay, so then the first thing, which is fun, of course, it has the black monophyletic bond in hyperbolic tilings. And you have to time, let me not go into too many details, but so if you put, I mean, one point of having such a tiling is that, of course, you have a finite cutoff because you can only go so many steps. And then the finite cutoff already has some implications on where exactly the similarities happen. If you're, so the dashed line here is the 2 that's the function in the center of the solution of the Van equation in the center here. And then if you go to approach the continuum limit, therefore the black line is actually an analytical quantity. If you for the continuum with just the cutoff, it approaches the 2 black monophyletic bonds. And so now what's very interesting, if you do this numerically for any of these tilings, so these are different tilings with different P's and Q's, they all follow exactly the same line. So there's some universal behavior. And that's very interesting. We're not quite sure yet why this happens. And one possibility is that there's actually a mathematical proof that whenever you have a tiling of a Euclidean, so just an AdS2 hyperbolic space, it's one just a tiling of a Euclidean hyperbolic space in 2 dimensions, then the boundary is always an S1. It's a sphere. This is a mathematical proof by somebody called, I think this is called the Gromov map. So this is one example, very simple example, I should say, of the Gromov map. And so because the boundary we recover just a simple S1, this seems to also have some implications on how exactly this limit is approached. Okay, I can't make this very concrete yet, but at least it's fun to see, observe numerically that this is missing. Okay, and then, you know, to make contact with our friends in electrical engineering, we can actually use Kirchhoff's law to write the Klein-Gordon equation in terms of capacity. I mean, with a capacitor and that is, so you can really have an amplifier space that looks like this. And then you can actually really calculate, so we haven't gotten them to measure it yet, but you can actually really calculate that if you actually sit on one of the singularities and you drive the system, then if you are below the bound, then you see a resonant behavior, and where it's above the bound, it decays again. Okay, so that's kind of cute. All right. How many more? I haven't. Okay, maybe I should come to an end and just say what we now did is to. Okay, so the goal is to have one theory at the boundary and one theory at the bulk, and show that they're doing to each other. So that will be the plan. Unfortunately, we didn't quite get as far, but we have some very interesting boundaries. We found a very interesting Hamiltonian at the boundary that reflects some of the bulk properties and has some very nice properties. In particular, we were able to calculate the ground state with Hamiltonian, and the way it works that we use the so-called inflation rule. So you start with a tile in the middle, And so this has these red corners, and they're red because they're in the same plane, they have two neighbors. Whereas the blue ones in the same and the preceding inflation step, they have three neighbors. So you have red and blue. And if you do this now in large number of times, then you end at the boundary, you end with some structure like this. So you get a so-called aperiodic spin chain, but nevertheless, which reflects the construction principle of your discrete part. And okay, so what we did is to actually find the ground state and then write down a tensor network which symbolizes the ground state. So we obviously the picture in the thing. Okay, so that's standard AdS CFT. Now what we did at this level is that we have a very nice model for a quantum chain at the boundary, so spin chain of the tiling, and we can actually find the ground state, and we have a tensor network that reproduces this in the file. So what we don't have yet is a good theory here that we can compare to, but now at present we are constructing something based on a matrix model, so that's some work in progress that I'm doing now. And so just to finish, let me show you the picture of our thing. So we can calculate the internal entropy. So these again compare the bulk and the boundary, but unfortunately, because it's recoupling at the boundary, we can't quite get the central chart correct yet. But so the green lines are the tensor networks, and so they kind of reconstruct our space. But the good thing about them is that they really are representing a true ground state for 220. Okay, and there's again some stories about how to implement the RD. And okay, it's nice to come, but I'm going to show the conclusions. All right. Okay, so that's the summary, but maybe to conclude, I will put those, so then there's some issues about the symmetries in this case, how to construct the gravity side, so there's some matrix models there. And okay, so if you're still around, I'm here this week, and then I'm again here the week of 2nd of October. So if you would like to hear more, then there's more things to do. And there, okay, there's some connection to matrix models. And okay, so we constructed this boundary function Hamilton reflecting the tiling structure. And so apart from the nice structure in holography, maybe there's also some implications for these hyperbolic neural networks. Okay, and so I come to the summary of my talk. So the messages I wanted to get across are this map between entanglement and geometry that started with Rio and Takamagi opens up new directions for the quantity duality and for quantum gravity. And so I showed this example of machine learning where classical information approaches also are also relevant for quantifying trainability in machine learning. So that was my first part of the talk. And so at the end, I turned to this discrete holography that may provide a new holographic quality example and potentially has implications for hyperbolic neural networks. So I managed, in this talk, there were a few guiding principles, and the various examples I showed, they managed to fit relatively well. So, there's this interesting relation between information and geometry, which can be of use for machine learning, but certainly is also interested in the context of the von Neumann algebra, the factorization puzzle, and then also here for the discrete. Okay, unfortunately, my talk started at 9 o'clock. Yeah. Never mind. Okay, but it's on YouTube.
Yeah, okay, thank you.
Okay, well, thanks for your attention.
Back to the beginning,
Yeah.
you talked about the two-dimensional Ising model.
Yeah.
Things didn't really work there. Can you say a bit more about that?
Yeah, okay, so the one thing what doesn't really work is to use this destination RG, because so we also, I can show you on the paper afterwards, if you do it in 2 dimensions, actually there's not monotonic behavior. It comes down after a while again, but that really shows that the approximation of this decimation actually doesn't work. And okay, I should have
Yeah,
Yeah.
some kinds of decimation work for the basic model that people want to know. That's what Canon did.
yes,
Wilson as well.
yes, but I mean they did it in a more advanced. Then you have this integration out. I mean there was no integration out in one. I mean I had a super simplistic version of integration out. Okay, and if you of course do the color knock way, I'm sure it's going to work, but we didn't do it. Okay, so the answer is we did a too simplistic approach in the paper, and we showed that in this too simplistic approach it didn't work. But of course, if you do the proper way, like color knock, it should actually work. But I'm happy to show you the figures.
They did it really helps. That's truncated. More non-local.
Yeah, that's true. Okay. Yeah, let me show you the picture.
Any other questions?
Yeah.